Okay, so we're back for the part two on September 10th of 522. I want to talk about this before the break. Well, we talked about the training MSE and the test MSE, and we said that the goal is to get the test MSE down, right? That's the big idea. But sometimes we have no test data. Okay, we have no test data. So what we want to do is we want to cross-validate, right? We want to cross-validate so we can get an estimate of the test MSE. There's techniques that we're going to look at in chapter 5 that help us estimate that test MSE using the training data. So this idea of like splitting the sample into like say 200 and 200 and cross-validating it in the best way, fitting it to new data, well, that's often not possible, especially with, data is expensive and let's face it, there's only so much time to get things done. So they've developed a lot of techniques, right, for cross-validation to try to estimate that test MSE, where you could actually use segments of the initial data set, and they're kind of really neat to look at, and we're going to look at those different options for doing that cross-validation. Again, remember, cross-validation is not only a statistical idea, it's a scientific one. Again, I encourage you as you're reading this stuff, you're trying to relate it to the science you're doing. And if we said, if you learn this just in the abstract, you say, well, cross-validation is a statistical concept, that would be unfortunate because no, cross-validation has everything to do with scientific kind of like replication, kind of like, well, the COVID vaccine works on a few people, right? But it may not work in the wider population. So if this is like the population of people we're testing it on, does it work on the wider population? Or does it just work on certain smaller samples? So that whole idea of cross-validation is really, really important. And we know what's going to happen with the COVID vaccine. We can almost predict it, right? They're going through many trials trying to get the COVID vaccine just right. And the reason why they have to do that is because they're trying to get the widest kind of set possible, the most cross-validation is possible. But we know what's going to happen. We can almost predict it. That this, they're going to say, yep, it works on a certain population, proportion of the population, whatever, and then, maybe someone's going to experience an adverse effect. And cross-validate it as you wish. It's not going to tell you everything about all data, because maybe there's something unique about this person in the form of an error term. Something about that error term that was associated with that person that's like, this vaccine isn't doing it for me, or it's having adverse effects. Science is a tough, tough game, right? It's really, really hard. And when you look at those biological sciences, they can't get away with much, right? Because boy, if that COVID vaccine doesn't work, there's real consequences. They can't go back to the theory and say, well, it's, my theory says this. They got to go the heck with theory. Somebody just died from the COVID vaccine. Yeah, but the theory says they shouldn't. Who cares? Here's the result, right? Here's the result. And we have to be aware that sometimes with other research, we don't get that. We don't get that result. We don't get that empirical finding. So sometimes it's very hard to know if the theories are right, because where's the validation? How do you know it's valid? It's a nice theory, but how do you know it's valid? Psychoanalysis has come under a lot of criticism for that reason exactly. And there was a lot of kind of blowback towards psychoanalysis because it's like, how do you prove it wrong? It sounds good, but how do you prove it wrong? Doesn't mean it's not useful, but it's really hard to prove wrong. On the other hand, behaviorism, you can actually maybe prove that a little bit wrong, but yet maybe it's too simplistic in the sense, right? People are reinforced and stuff like that. It's like, I don't know. Maybe that's true of the pigeon or the rat, but maybe people are more complex. So science is really, really hard. The bias variance trade-off is important. Okay, so when we look at statistical learning methods, there's a couple things we want to kind of optimize when we talk about these test MSE curves. So getting MSE down. So it's possible to show that the expected test MSE can be decomposed into the sum of three fundamental quantities. And those quantities are the variance of the method, the squared bias of the method, and the variance of the error term. So here we have the expectation of y sub naught minus the predicted value by the function. Whether that's in linear regression or some other thing, you're generalizing that term. Observe by what does the function say we're going to get? Predicted, hat value. Well, that's equal to the variance of the function, not the data, right? The variance of the function plus squared bias minus the variance of the error term. So this is the expected MSE and refers to the average test SMSE that we'd obtain if we repeatedly estimated F using a large number of training sets. What does that mean? We're using a large number of samples. Expectation of the variance is equal to the variance. It's the same idea for the simpler variance. This expectation means on average, if we did this over and over and over on a whole bunch of samples, and you may remember that as frequentist probability. Much of these ideas are based on frequentist probability. The idea that if we do it over and over and over, what's going to happen? Average this over all possible values of x sub naught in the test data. So it's a function of two things. So in order to minimize this, which is our goal, we want to minimize this, almost like minimizing the sum of squared errors in regression, right? This is like the wider idea to that. In order to minimize the test error, we need to select a statistical learning method that simultaneously achieves a low variance and low bias. But the variance is inherently a non-negative quantity. It's non-negative because this can't be negative. Observed minus predicted, you're squaring them. You can't get negative there. Some weird cases in some statistical models, you get a negative variance. And that's where you need to go to your supervisor and say, I got negative variance. And you should get a weird look. What do you mean by the variance and bias? What I mean is that there's usually a problem if you get a negative variance. What do you mean by the variance and the bias of a statistical learning method? Okay, variance refers to the amount by which the function would change if we estimated it using a different training data set. So I want to highlight this, it's important. This isn't how much the actual data would change. This is by how much the function would change. So it's fair now to talk about a statistical learning method as saying, that method has high variance. This method doesn't have high variance because you're relating it to the function. Since the training data are used to fit the statistical learning method, different training data sets will result in different functions. Okay. But ideally, the estimate for F should not vary too much between training sets. That's kind of ideal. We don't want it to vary too much. But if the method has high variance, right, the method has high variance, then small changes in the training data can result in large changes in the function. More flexible statistical methods have higher variance. That kind of makes sense, right? Because if you have a highly flexible statistical method, in other words, you can fit like a whole bunch of parameters and tweak it and stuff like that, you bet that's probably going to have high variance. Small changes in the data are going to generate, right, higher variance. So, this has got quite a bit of flexibility to it. Well, if I generalize this to another data set, well, maybe this even would suggest an entirely different curve. That's not a bad thing if my function isn't capturing that, because maybe the phenomenon is actually different. But if I have something similar to this, and the curve goes here, but there's a small change like this, this one's a little bit different than this value, well, maybe the function has quite a bit of high variance, and that's not necessarily a thing we want to have. Okay. So consider if you look at figure 2, you can see examples of that. The flexible green curve follows as high variance, 2.9. Got to go back. Right over here. That flexible curve, has quite a bit of high variance because that's a pretty complicated function, whereas that linear least squares is going to have relatively low variance. So you want these things to have low variance. It's usually a nice thing to get. On the other hand, the bias refers to the error that is introduced by approximating a real-life problem. So what does that mean? Well, the problem may be extremely complicated, yet you're fitting a very simple model to it. So for example, linear regression assumes that there is a linear relationship between y and your x values. Do you think that really exists in real life? Do you think it has such a simple linear shape? No. So it's going to result in some bias in the estimate of the function, right? In other words, it's got low flexibility, but it's biased, right? Here's, the example there. There's the mean. High bias. That's not going to describe the real life situation in most cases. You're going to have high bias in the estimate of the function. Example, if it's substantially nonlinear, then no matter how many training observations we're given, it's not possible to produce an accurate estimate using the linear regression. In other words, linear regression results in high bias in that example of 2.11. More flexible methods result in less bias. So if you have a lot of observations and you are trying to fit too simple of a form to it, you're trying to fit too simple of a form to it, you're going to have high bias in there. So as a general rule, as we use more flexible methods, the variance will increase and the bias will decrease. So, high bias. You're just fitting like a horizontal line to it. As you use more flexible, so maybe your data look like this, I'm going to go ultimate flexibility here. So I've got a lot of flexibility. Well, the variance increases, right? So this second method here, I'm doing this, exaggerating a little bit. Well, the variance is increasing, but the bias is decreasing. Now, why is the bias decreasing here? The bias is decreasing because this is a little bit more representative of the real world idea that they're talking about up here. So they're saying, the idea is this. The idea is this represents more of maybe what you're going to actually find in empirical reality for this particular situation than the horizontal line. So if you use more flexible methods, like fitting more parameters, more complex splines and stuff like that, the variance increases, but the bias will decrease. So there's a trade-off between the two. So we talk about a method as saying high variance and low bias. It's a trade-off. We talk about the relative rate of change of these two quantities determines whether the test MSE increases or decreases. And as we increase the flexibility of a class of methods, the bias tends to initially decrease faster than the variance increases. But there's patterns to these things. So let's look at figure 2.12. Blue collar, where are we? 2.12. Oops, right over here. Okay, so here's different situations where you have squared bias is in the blue. So there's your squared bias going down in terms of the flexibility. And then you have the orange curve over here is the variance. And then you have the variance here is the dashed line. So the test MSE for 3 different data sets in these particular problems, we see the vertical line indicates the flexibility level according to the smallest test MSE. So look at what MSE is doing right here. There's the lowest, right? And this is on for 3 different data sets in those previous figures. There's the lowest MSE, and there's the lowest MSE. And you look at these different situations, and you have different amounts of bias and variance over here. So it's going to vary a little bit. Okay, it's going to vary. Bias and variance are going to vary across the methods that you use, and it's showing it for 3 different data sets. right? So it's going to vary a little bit on different sets of data, whatever gets that MSE down. So 2.9 to 211, you refer to those, and um, this one here is for the linear. In this setting, a linear regression provides a very poor fit to the data. So they're showing operating that linear equation on that data. Well, there's your bias over here, according to the flexibility. So different data sets provide different bias and variance. You can look at those data sets as well. And we'll unpack that more as we go. When we say this method has high bias, this method doesn't, you'll see the differences. The relationship between bias and tests is given. So as the bias variance trade-off, good tests set performance of a statistical learning method requires low variance as well as low squared bias. That's the ultimate. If you can get that, that's really good. But it's a trade-off because it's easy to obtain a method with extremely low bias but high variance. Okay, so look, extremely low variance but high variance by drawing a curve that passes through every single training point, as we just said. It's got high variance, but it's got low bias, right? And that's what we're talking about. It's got low bias here, but the variance is high. Why? Because, boy, when you apply that to the next sample, that's not going to really work very well, right? That's not going to work very well, even though when you're drawing that curve that passes through every single training observation, as the authors are talking about, they're saying that might actually be a little bit more reflective of reality because you're actually like describing the phenomenon in that particular sample a little bit better. So it's a trade-off between those two. And you start to think of it as that idea of going from data set to data set. And again, I'm doing this kind of trivial case of attaching the points like this, but to say, well, this is maybe representative more, a little bit more of a reality of what's going on because it's based on the actual observations. But boy, that's gonna have a lot of variance, high variance, because it's passing through every single training observation. Yet, on the other hand, I mean, this is bad, but this is not that great too, right? That's not great because, boy, that's going to be like not corresponding to anything in reality, really. Right? So that's going to have a lot of bias. In other words, you're not really estimating well if you're just doing this. So when you think of it, what's the trade-off? Well, the trade-off is going to be maybe, I don't know, something like this, some kind of curve that goes through there that we're going to say, okay, well, this method is going to produce, is going to kind of try to minimize those two things, right? And when you minimize those two things, well, you're trying to get this to the lowest level. And this is quantifying in a simulation study where the bias and the variance end up for the lower values of the MSE, depending on the situation we're dealing with, right? So you look at this and you say, well, for me to minimize MSE, how did it turn out for the variance and the bias in this particular situation? When I lowered MSE, what were they like over here? And when I lowered it, where were they like over here? So it's going to vary a little bit. But we see that we like them both to be low because that's going to minimize our fitting function. In the real life, here's the bummer though, right? In the real life situation in which F is unobserved, it's generally not possible to explicitly compute the test MSE bias or variance for a statistical learning method. So in the real situation, this is simulation here. What they've done when they're showing those curves is simulation. So you can't actually get that from the real data. So you're not doing it on data and saying, hey, how's my bias doing? How's my variance doing? This is on simulated data So you're going to have trouble actually computing these things to get the MSE bias or variance. Now, I want to make a distinction here because it isn't entirely clear. When you say the variance for a statistical learning method, now, here, the problem is this. We say it's for the method, and the authors are correct in saying it's for the statistical learning method, but things will behave a little bit differently across the data that you're dealing with. Okay, so we don't want to say that one method is always, it's kind of like saying one method is always the best under every circumstance, right? It depends a little bit on your data. Like, if I have data that look like this, and I'm doing this, well, that may actually be a good strategy for that particular situation. But if my data are very, very scattered, or maybe there's a nice functional form to it, then this becomes a poor strategy. So it also has to do with the actual data you're dealing with. But keep it in mind, the bias variance trade-off. So when we talk about this procedure as high bias and low variance in general, that's what we're talking about. Doesn't guarantee that it'll outperform much simpler methods such as linear regression. And again, the word is it doesn't guarantee. Sometimes these things outperform, sometimes they don't. That's why we were talking about earlier. Sometimes we apply them to a whole bunch of different things, apply different methods, and kind of see what fits the best. So if we take an extreme example and we assume that the form of the function is linear, in this situation, okay, you see, in this situation, do you see how important in this situation is? If the true functional form is linear, like what I'm trying to draw here, this is like a horizontal thing. If it's linear, linear regression will have no bias, making it very hard for a more flexible method to compete. Right? Why would you use a more flexible method if the true function is linear? Now, what's the true function? The true function is dictated in this sense as what the data are like. So if the data are actually like this, the true function is this. This is the truth, right? This is the truth. Then in this particular situation, data, in this particular situation, linear regression will have no bias because the true function is linear, making it very hard for a more flexible method to compete. So in other words, why would you use a more flexible method if that linear regression is doing a great job? But if the true function is highly nonlinear and we have ample number of training observations, then we may do better with a highly flexible approach. Like, I keep going to polynomial regression. I keep trying to attach the dots, but there's other techniques as well. So I just want to repeat this last point. If the true function is highly nonlinear, so if in truth the function is nonlinear, so if in reality, right, if out there in reality the function actually is like this, right, and we have a number of training observations. So again, we have a number of training observations that we can fit this to, so we can actually get the actual pattern down. Because look, if you don't have training observations, you're never going to detect this. So if I have this, but the true function is this, then I don't have enough training observations. That's why this is important, that if you have enough training observations, you will actually be able to detect the true functional form using a highly flexible approach. That's what that's talking about there. So that's why the situation is important with what you're dealing with, which is why earlier when we looked at those graphs, things change, at least in the simulation, things change a little bit depending on the situation that you're dealing with. So that's important as well. has some characteristics as to what the true functional form is. So you see there's a hypothetical here, right? Is often we don't know what the true functional form is. That's why we're fitting the model. So, I mean, the kind of, the big picture here is you're fitting a linear regression. Well, does it have high variance or high bias? I don't know. It depends. What's the assumed situation? What's the assumed functional form that's at work? And if we don't know that functional form, it could be really, really hard to know. That's why you may fit one method, it fits well, another method doesn't, but you generalize it to the new data set and it turns out to be a disaster, whereas one does better than the other. This is always at play, and that's why they're always talking about the idea that we actually don't know these things, but you keep them in mind as you're doing it. And a lot of it has to do with, you keep these simple examples in mind and say, if I'm fitting a really easy functional form, or at least it's assumed to be an easy functional form, maybe prior literature says the relationship between drug dose and healing is linear. Well, then what's the point of using a really complicated model, right? So, if you kind of know it's going to do this, I'm not quite sure the point of trying to fit this to it. Just make it linear. It's going to be a lot better, both in terms of generalizability, and it's going to be a simpler function to actually interpret, because you're not like adding in all these squiggles, which is probably just like error anyways. Okay, so complicated in that sense. It's one reason why in the first regression course, sometimes people are like, hey, how about we use something really sophisticated on that? And it's like, no, you do that, it's going to change the next time. It's going to change the next time. You're not going to get that. You're not going to get that solid theoretical backing for using a different function as you would for the function that you're using. So oftentimes simpler is better unless it's complicated. But even if it's complicated, just to return to this point one more time, even if it's complicated and the functional form is a complicated form, again, I'm exaggerating by connecting the dots, but you get the idea. If this is the true form, then you definitely want something that's flexible, right? It's got some bends in it to capture that. But again, as the writers are saying, that assumes you have the training observations to detect that. If you don't have the training observations, you won't be able to detect the functional form. Okay, that's a big idea, and it's actually a little bit of a hard idea to wrap our heads around, because we assume, let's take it to the extreme here. Just bear with me for a second. It's kind of a scary thought, but look. There, you fit that, you fit your regression, you say, hey, look, I got an R squared of like 0.60 and everything's good, I'm going to publish it. What they're talking about when they're saying when the number of training observations is sufficient is this idea. You don't know what's going to happen in the future. So you have a small sample. This person the vaccine doesn't work on. You get the analogy? This person the vaccine doesn't work on. Therefore, you have to make sure you have sufficient observations so that if the true form is a weird form, you actually have the data to detect it. Clinical psychology, you observe your client for a week, you think you have it figured out. Well, maybe there's something I'm exaggerating, but maybe there's something you haven't noticed. Observe for longer. Get more training instances. Maybe it's a more complex thing than what you're seeing in this shorter span. Analogy, maybe the theory that you're applying to the clinical observation is not sufficient. It's more complicated. You say, you know what? I'm going to pick on the psychiatrist first. We like picking on psychiatrists, right? So the psychiatrist says, oh, you're depressed? Here, just take a bit of Zoloft. You'll do better. No problem. It's an easy one, right? Straight line. What's the problem? The problem is that there may be more to it. It may be more complicated. But in that 1 hour interview where you had to fit a functional medicine to the problem, you did not detect the full complexity. So in other words, by analogy, the psychiatrist, our criticism of the psychiatrist would be, no, 2 months of therapy is necessary because you're seeking to capture a more complex functional form. It's not as easy as what you're seeing in the hour. I think that's a powerful analogy here. It's a powerful analogy to kind of compare these methods. So, if we say right here, right, in this situation, linear regression will have no bias. Well, it has no bias by giving the person medication if the true functional form is linear, simple, right? Just a little down, a little medication will help. You'll be better and you'll be back on your feet. Do you see the analogy, right? In other words, making it very hard for a more flexible method to compete. What's the analogy? Can you see the analogy? Right? So, somebody comes in, I'm feeling a little bit down and a little bit of boost, going through some things in my life that I could, just get through. Well, a little bit of medication might be appropriate to help you get through. Why do you need 2 years of psychoanalysis when the problem is you may not be, your blood pressure balance may be off a little bit, or your glucose levels may be off? This is a perfect example. If you watch Frasier, it's a perfect example of this. Frasier's on his radio show and someone's saying, I'm feeling down in the morning. He's like, well, you have a complex thing. It must be related to your childhood. You're going to need years and years of therapy to overcome this. And it's your fear of leaving the house and all kinds of complex things, right? Whereas the other person, they had the medical doctor on there. The medical doctor is basically saying, you know what? The true functional form is probably pretty simple. Whether it's linear or not doesn't really apply, but it's probably pretty simple. In other words, don't make it more complicated than it needs to be. Eat some protein in the morning and you'll feel better. You see the analogy, and it's a powerful one. It's a powerful one, and it applies there. Okay. But if it's truly high nonlinear and complicated, well, then you need the training observations. So in that instance, Frasier would say it's not just the protein. This person has deep-seated issues that need to be dealt with, as you will see in the next radio program when we listen to the person again. But how do you know what the true function is? You don't. You have to have knowledge of the research area, which it kind of circular, right? The method you use and the complexity of the method has to depend on a little bit of what you think is going on underneath. And that's hard to know. So I hope those analogies help. The classification setting, well, this is a situation where we have indicator variables. So we're trying to make a prediction into the right class. Indicator variables, you have either goes into one category or it goes into the other. We usually have a predicted category where we say 1 is going to be what we're predicting and 0 is going to be the other category. Well, we want this because those variables are sometimes not continuous, right? So you have a classification. You want to classify into survived versus not survived. Now, when you make things binary like that, that's a whole different thing, right? It's sometimes you have continuity in your, or pseudo continuity, and you want to say, well, let's make it binary. Be careful, right? Be careful about making things binary. Huge decision. You want to discuss that with your supervisor and say, well, should we make this binary or should we just keep it continuous? And you guys should spend a long time on that, because that's important of how you measure it. Again, it's a measurement issue, how you measure that particular variable. Okay, so it equals 1 if it's not equal to that, and 0 if it's equal to that. But it doesn't matter how you code it. I can code 0, I can code 1, depending on which one you want to model. I can model heads, I can model tails on the coin. It doesn't matter. I'm going to basically get the same result. It's just which one do I want to deem a success versus a failure, to use the binomial analogy. Okay, so we have the training error because it's computed based on the data that was used to train our classifier. So how many times does it hit the category? How many times does it doesn't? And you're taking that fraction of how many times it gets it right. So does it classify things 60% right, 40%, or what have you? The test error associated with a set of test observations of the form given new observations So you're giving you observations, you're giving a new X, you're giving a new Y. Well, that's the average of how often it doesn't hit it. So Y prime here is the predicted class from applying the classifier. Call that a classifier because you're trying to group into like two categories, one category or the other. And a good classifier is one for which the test error is the smallest. I mean, that's a lot of complicated stuff to complicated notation to say, does it get the hit rate right? Right? Are you classifying more often in the right category than in the wrong category? Right? If I have a function rule, and I say, well, the function rule is good, is it predicting right? That's analogous to the regression idea, where you have continuous data. It's just that here you have a binary situation or a multinomial situation where you're dealing with categories there. Okay. Right now, I'm just going to skip over this because I want to end pretty soon, but I'll talk about the Bayes classifier a little bit more next time to clean up the chapter. I'll just briefly mention the k-neighbors as well. But I just want to just start into chapter 2 because most of chapter 2 is just review, and I'm just going to run through some of this and highlight some of the important places, but most of this you all know from regression courses. So there's really, because I want to start getting into chapter 4 next week, linear regression. All of this is familiar, relationships, etc. How much does media contribute? Be careful on the action words, right? The effect, again, we know that. Be careful. Y is a function of X is a mathematical statement. Doesn't mean anything physical. And I know that sounds simple, right? But boy, when you apply that to real data, and you hear researchers, I mean, they take that mathematical model and they start making conclusions. You say, you can't say that. You can't say that. I mean, you got to be like Dr. Fauci, right? Dr. Fauci on TV. You know, he's always the one who's saying, Dr. Fauci and Dr. Birx, right? They're always going to say, well, wait a minute, we don't know that. We don't know that. They're almost like, you have to be a minimalist. If you're to be a good science, you have to say, we don't know that. We don't know that. What do we know? Barely anything based on what we've done. There's a lot we don't know. There's a lot we don't know. And you can see that in like the biological sciences with the vaccine. That becomes real, right? Does the vaccine work? We don't know yet. You can't pretend it works because, boy, then people will start dying from side effects. So you have to apply that, always have a healthy skepticism. Doesn't mean you're being pessimistic. It means you're got to be a healthy skepticism. And you can often spot good scientists from not so good scientists by that idea of that, like a minimalist perspective, saying, well, we don't know that. We don't have the database for that. In the Challenger disaster of 1986, when the Challenger exploded, if you look that up, you can see the explosion on YouTube. The engineers apparently for NASA were saying, you know, don't launch the shuttle at 31 degrees Fahrenheit. The management was saying, why not? All other launches have worked. Yeah, but all other launches were taking place at 51 degrees or higher. So the management is like saying, apparently, come on, it doesn't matter. So it's a little bit cold and there's icicles on the boosters. Well, what did the engineers apparently say to the management the night before the launch? Apparently, they said, we don't have the experience for the statement you're making. We don't have the experience for the statement you're making. So we've launched most of the shuttles at 51 and up. You want to launch at 31. May not be a big deal to you, but it's a big deal to us. This experience, we don't have it. So what did management do? Management said, yeah, well, we want to keep to our schedule, right? We want to keep to our schedule. They launched it and it blew up. The engineers knew, apparently, that the shuttle was going to blow up. They expected it to because they had some prior data to say that at low temps, the booster is not going to be able to hold in the gases. So that makes a difference, right? Extrapolation. Drug dose 1, drug dose 2. Hey, if you take drug dose 1, then drug dose 2, you'll just increase. Wait a minute, I just drew a line. I don't know if that's going to happen because I don't know what happens in between. I don't have a database for that. Maybe you can guess that it's going to increase and be linear, but you don't know. So you got to be very careful. Dealing with interactions, you can have interactions of regression. Yeah, wow, synergy effect, right? Yeah, wow, it's the big complicated word, synergy. Sounds like something physical. No, it's just variance partitioning until it is physical. Of course, that came up in the marketing literature because they want you to think there's synergy going on, which there may not be. Even interaction's a bit of a stretch, but we got to describe it somehow. But just know that simply because you find an interaction in regression or ANOVA doesn't necessarily mean anything's interacting. Which begs the question is that when you do things like mediation and you call it moderation, doesn't mean anything's mediating or moderating anything else on a physical level. It means you've done statistical mediation and statistical moderation. It doesn't mean that your model is all of a sudden uncovering physical processes in your data. Really, really important, okay? Dr. Fauci is not going to buy that. Dr. Fauci is going to say, where's the physical representation? And you're often going to have to return back to your statistics on it and say, well, there's a statistical model. Yeah, but the statistical model doesn't necessarily describe a physical process. The statistical model itself is an abstract thing applied to empirical data. These are not like unimportant questions. This is the big picture of what you're doing and whether what you're doing makes sense. So really, really important. We know all of this stuff, estimating coefficients, least squares criterion, there it is. Yeah, no problem. There's your minimization of the sum of squares. These formulas are great, right? Like you got the estimated slope, the estimated intercept. We can unpack those. You've probably all done it to some extent of how these are kind of set up, least squares estimates. This shows what's known as a contour plot where the intercept and the slope is here, and these are corresponding z-values of that distribution. So it shows, in this case, where this is joining the intercept and the slope over here. And what happens as you go up in the intercept and up in the slope over here, where you go on the grid of those z-values. Minimization of the error, there's the point that minimizes the sum of squared errors. And we have to put it like this because we have a kind of like a three-dimensional thing going on here. But you can also look at it as the bottom of a parabola, right? This is just more complicated three-dimensional thing, but that's where the minimization occurs over here. Okay. Accuracy of the coefficients, expected value, we know all this stuff. Careful, expected value of y, right? I put average, it's expected. It's not the value of y when x equals 0. We're doing statistics, so we got to account for this little guy here. So it's the expected value. It's not the value. It's not 101 math. It's statistics. So you got averages and expectation and all those things. Population regression line, all is good there. Here, when you fit different lines, you get slightly different things. So you get a little bit of a randomness. Some of you may look at that and say, hey, that's almost like the random slopes idea, right? How much variation do we expect in the slopes in the randomness when you do things like hierarchical linear models? So random sets of observations produces random regression lines. And if you deem the slope as a random effect, you can expect that regression line to bounce around a little bit. Population regression line is unobserved. We usually don't know what it is. That's why we're doing it. Now, if you think of it, the population regression line is unobserved. It's kind of like what we just said earlier. F at x is unknown. Okay, if f at x is unknown, then you don't even know what you're estimating, so you don't know how complicated of a procedure to use, because you don't know if the data does this or if the true functional form is this, which again goes back to our previous point, that if you use an overly complicated method, you may be using it on something like this, which makes no sense. But in some cases, it does make sense. So what's the important point? You cannot do statistics. You cannot do these models without an intimate area of the research area. You have to know the research area and even sometimes have a hunch of what you're going to see before you even choose a method. Okay. Biased, unbiased. We like estimators to be unbiased. Remember, we like intercept and slope. That's why we calculate those things. They give us nice unbiased estimators. Sample variance with a correction of n-1. The denominator is unbiased as well, et cetera, et cetera. That looks familiar, right? Standard error of the mean. For those who have taken my 520, for those who haven't, you've probably seen this before as well. 520, we talked about this for like 2 months. what happens is you increase n, decrease, so you get variance of the mean, etc. There's your standard error of the slopes. Intercept. The intercept is b sub naught here, and there's the slope. We could talk a lot about these formulas, but we know what the standard error gives us, right? How much variance do you expect to see under the null hypothesis? We see that the standard error of the slope is smaller when the x's are more spread out. Makes sense. It's smaller when they're more spread out. So if you increase the spread here, well, you're dividing this by a bigger number, so it gets smaller. Residual standard error, we know that from the regression. You get that residual standard error, divide by degrees of freedom, and you get the MS error, right? That's good for regression. Confidence intervals, we're okay there. Always be careful about confidence intervals. It's the parameter that's fixed. It's the sample on which you're computing it, which is random. So 95% of those intervals computed on the samples that you get are expected to cover the parameter, right? Confidence intervals are nice because they show you the precision of the estimate. Right? You want what's better? Narrow confidence intervals are better than wide ones. Hypothesis test for your slope. There's some relationship. There's your alternative. No relationship. No problem. There's no relationship between x and y. There is some relationship between x and y. But again, remember all the effects of sample size, the p-value. Be wary about the p-value, right? There's a relationship. Yep, I can get an F test to reject. I can get this out of here if I have a large enough sample size. So remember, you're looking at the data. You have to be aware of the influences of sample size. There's your t-statistics on your regression coefficients. No problem. Usually this value is 0 unless you have good theoretical evidence for why it shouldn't be. You could even set it at a different value, usually not. P-values, there's like a lot. We've talked about p-values. For those who have taken other courses, you're coming from really good courses, you know what the p-value indicates. Be careful, be careful. You see p is less than 0.05, that's the start to things, that's not the end, right? You never want to associate p is less than 0.05 with, hey, we found a COVID cure. Wait a minute, right? Wait a minute. P is less than 0.05. Stop. What's going on? Right? I need to know more. And that's really, really important. Okay, if you're not interpreting, if you don't know those issues on p-values, be careful, and then you will see when you work in other contexts, a lot of researchers are not familiar with that. And you have to be the one to say, wait a minute, if p is less than 0.05, don't get all excited. There may be something going on here, and dig into it. Don't be skeptical, but be critical of it and say, let's look at our sample size. What's going on? Wait a minute, there's nothing going on. It's just like the oxidative stability of the oils. Olive oil is better. Olive oil, don't use sunflower oil. Wait a minute. Sunflower oil is not going to break down until an hour later anyways. I'm going to use sunflower oil. It has higher utility for me. So this ranking system doesn't really make sense in terms of what I'm actually trying to study. If you just rank it, you say olive oil is better, then you walk away thinking olive oil is better. Use olive oil, not necessarily. So we know all of this. That's good. Accuracy of the model, residual standard error, estimate of the standard deviation of the error. There's the formula for it. And we've talked about all of this in previous courses. There's your R squared, 61% variance explained. There's your F, R squared statistic proportion, all the caveats about R squared, careful about R squared. R squared of 1 doesn't necessarily mean you've got a causal agent, right? It's all those big picture items where things can go astray. I've got an R squared of 1. I've determined the causal factor, not necessarily. I don't know if, nighttime causes morning in the morning. It's weird to say so, even though you get an R squared of 1. So be careful. Proportion of variance explained. Again, what's a good R squared? Well, that depends on the application. It depends on the application, but you can also evaluate R squareds in terms of their absolute magnitude as well, right? Like this is kind of a point of view. I've been kind of taking this point of view a little bit recently as well, because sometimes people will report an R squared of 0.20, And they'll say, you know what, this is pretty high in my field. Okay, that's great. What are you getting in your field? Other people are getting 0.15. Well, I got 0.20. Well, that's impressive in your field, but it's still on an absolute level not that impressive, right? And sometimes you see research where I worked with some researchers before at a very, very prestigious university. I'm not knocking the big schools, but I'm just saying that this could even happen at the big schools where they had an R squared, I'm not kidding you, of like 2 to 3%. Like they were explaining 2 to 3% in a non-experimental design to boot. They're just throwing variables in, doing a regression, and they got an R squared of like 2%. And they were amazed by it. They were amazed by it. It was so impressive. It's like you're hardly explaining anything. It's almost like if you're getting an R squared of 2%, most likely your experiment, well, the study, it was an experiment, is probably not even worth even mentioning. But that's hard after you spent a lot of time in it. So beware of those, what's a good R squared and what's a small one. Correlation, that should look very familiar. You should be able to unpack that in terms of what's going on, cross product, and you've got a square root of those square deviations there. Multiple linear regression, very important stuff, right? Some of the stuff we're going to look at in the course as we go forward are going to be generalizations of multiple regression. So make sure all of that stuff is clear. What are you doing when you're interpreting these parameter estimates? Is this the effect of TV on whatever the independent variable is? No, it's not. That's not the effect of TV, right? That's the effect of TV in the company of this. Very, very, very important, right? So it's only in the company of this. If you analyze TV separately, this relationship may change. It may not be statistically significant. It may be, and that's the basis of those like moderate mediation relationships. But again, the mediation could just be happening in terms of variance partitioning unless you have a statistical or a substantive theory to back up your mediation. More stuff here. Does it explain? Well, what does explain mean? Does it fit? We're okay, training data there and all these things. There's your null hypothesis. There's your F. And that's pretty much it. Now, here's the thing that when n is large, an F statistic that is just a little larger than 1 might still provide evidence against HO, right? That's, again, the p-value issue. It's a big thing. They mention it like in 2 lines. But from a scientific point of view, that's huge. From a statistical point of view, it's interesting. But from a scientific point of view, it's really, really important. Okay. What others? This one looks important. If we use the individual t-statistics and associate p-values in order to decide whether or not there's any association between the variables and the response, there's a very high chance that we will incorrectly conclude there's a relationship. What they're getting at here is that you expect some of those betas to actually reject the null. That's why you have to look at that overall F. The overall F doesn't quite work that way. So you definitely want to look at that overall F before you look at tests on different predictors, because that overall F is like a global test, right? It doesn't suffer from the problem of this scary face over here because it adjusts for the number of predictors. Otherwise, you could actually get a few rejections on individual predictors, but as they're saying, there may actually be due to chance possibilities. Okay, I think that's enough for today. I'm going to continue this. We're also going to go through the Bayes classifier and talk about the a little bit more on classification next week from the previous chapter as a cleanup. And we're going to talk about this in terms of variable selection and importance of variables and things like that. And then we're going to get into chapter 4. So we've covered almost all of chapters 2 and 3, a lot of review in chapter 3. And then next week we will be into chapter 4. And chapter 4 deals with the classification. So probably have another good, maybe up to 2 hours next time to get through some of that material. Okay, so that's it for today. We'll see you next time.